Hello, student. Welcome back to this topic of digital electronics. So, in this session, I am going to explain the working of a counter type of analog to digital converter. In my earlier session, already I have discussed different kinds of analog to digital converters and digital to analog converters. Depending upon the situation or depending upon the applications, we may be in need of either ADC, analog to digital converter, or DAC, digital to analog converter. So, a counter based analog to digital converter is a high resolution analog to digital converter, and it uses only one comparator and could be constructed with the help of a variable reference voltage source. As you know, in other ADCs, the reference source voltage was a fixed one. But here, in order to increase the number of bits, we are using a variable reference voltage source. So that is the idea. And to construct this type of converter, a simple binary counter is taken and the digital output signals will be taken from this counter, and thus it should be an n-bit counter. So here, as you can change the reference voltage value, so this counter becomes the n-bit. So any value of the input voltage can be given to this circuit, and where this n is the desired number of bits. And because of this reason, because of the higher values of bits present in the circuit, it becomes a high resolution circuit. And the output of this counter is connected to a standard binary ladder to form a digital to analog converter. So I will show you the circuit. So here, even though it is ADC, analog to digital converter circuit, a part of this circuit is DAC. I will explain why this DAC is needed in this circuit. And if a clock is now applied to the input of the counter, the output of the binary ladder is the familiar staircase waveform, and this is exactly the needed reference voltage for the comparator. The block diagram is as shown below. So this is the block diagram of this counter type of ADC. And you can look at this start line is here. So when you switch on the circuit, all bits are always set equal to 0. And sometimes, like in successive approximation counter, the MSB goes 1, but here that kind of things are not going to happen. So when the circuit is switched on, all the bits are set into zeros. So here clock is here. This is gate and control system. Generally, an AND gate is used here for the purpose of gate and control. Simply, it can be an AND gate. So it's not a big circuit. And here, this is the block diagram shown in the dotted line forms the digital to analog converter. So it is ADC, analog to digital, but we need DAC also. Here, why I will tell you. This is simply a DAC, digital to analog converter. It consists of a binary counter here, and n number of lines, means any number of bits can be there. These are the level amplifiers which correct the voltage levels, and the output of this is fed to the binary ladder, and output of this binary ladder is fed back to this comparator, the negative terminal or the inverting terminal of this comparator. And the input voltage, which is to be converted into digital, is fed to the non-inverting terminal of this comparator. So this is the comparator. This is the comparator, only comparator present in the circuit. So why this ADC, DAC is required here? Because the voltage what we are supplying here is the analog voltage. This is the comparator. So the comparator always compares the two signals of the same kind. So as it is an analog voltage, we need another analog voltage like reference voltage here. So two analog voltages are supplied to this comparator, and a differential voltage appears at the output of this counter. So when there is a differential output at the output of this comparator, this gate and control circuit becomes activate, or we can say that the gate becomes open, and a clock source is connected here, and this clock source is generally a square wave generator. Most of the time it produces the square waves of high frequency. So those square waves or cycles are entering this gate, and when there is an output at the comparator, so this gate is open, and all the cycles are going to the counter. So I will explain this operation level completely. The operation of the counter is as follows. First, the counter is reset to all zeros, as I told. The counter is reset to all zeros means all the bits will be at a zero level. Then, when a convert signal appears on the start line, the gate opens and clock pulses are allowed to pass through to the input of the counter. The counter advances through its normal binary count sequence, and the staircase waveform is generated at the output of the ladder. So this waveform is applied to one side of the comparator, and the analog input voltage is applied to the other side of the comparator as I explained. So when the reference voltage equals or exceeds the input analog voltage, the gate is closed and the counter stops and the conversion is complete. The number stored in the counter is now the digital equivalent of the analog input voltage. So all these things we can see here. This is the circuit. Start line is here. Start line means when you switch on the circuit, all the bits will be at 0, 0, 0 level. It may be 2-bit, 3-bit, or 4-bit, whatever it is. And input signal is supplied to this this end. Actually, it is the non-inverting terminal of this comparator. And the inverting terminal of the comparator is fed with this reference voltage. Now I will explain how the digital, this analog voltage is converted into a digital. And when analog input voltage is applied to this comparator, and immediately the counter, the start line also starts and clock also starts, and counting starts here. This is a binary counter, and accordingly the voltage is sent through this level amplifiers and to this binary ladder, and this binary ladder converts this output of this counter into an analog voltage. So this digital to analog converter converts the signal into analog. So here is a familiar staircase wave reference voltage is produced here. Why this staircase wave is produced here? As the counter counts the clocks, the voltage level increases in the circuit. So that appears here in the form of staircase, a well-known staircase form. So in the inverting terminal of this computer, this comparator, the voltage level also increases. And this comparator continuously compares the input signal and this reference voltage signal. And when this analog input voltage becomes exactly equal to this reference voltage, the differential output voltage at the output of this comparator becomes 0. So when the output of the comparator becomes 0, this gate immediately switches off. So this gate opens whenever or until there is some output in the comparator. Up. So when the comparator output goes 0, the gate closes. So in that way they works. So the voltage level, this reference voltage grows until it becomes equal to the value of this analog input voltage. Once it becomes equal to the analog input voltage, the output of this comparator immediately goes 0, and this gate closes, and the clocks produced in here in the clocks part, they cannot go through and reach the counter, and because of that reason this counter stops working. And as you know, this digital to analog converter also has the have some flip-flops inside it, so that it store the resistors. So this digital to analog converter is also have some register for the storage of information, and the output, the reference voltage, when this reference voltage, the digital outputs are taken from this binary ladder, and when this reference voltage exactly becomes equal to this analog voltage, the gates also closes and this also stops working, and the digital output appears across this binary ladder. So this digital output is stored in a register. So in this way, this counter works, and it is a very simple way. And this reference voltage is produced until it becomes equal to this analog input voltage. It is a very simple way. And same thing is explained here. I have explained all these things. And this converter is composed of a digital to analog converter, which is shown by the dotted line. As I explained, it is needed to produce the analog voltage in the staircase waveform, and that voltage is always or continuously compared with the input analog voltage. So a digital this DAC is formed with this DAC is required for that purpose, and a comparator is there, a clock is there. A clock means generally it is a square wave generator, and the gate and control circuit is there. As I told, this gate and control is most of the time as simply an AND gate, and therefore this is actually a closed loop control system, because closed loop is there. An error signal is generated at the output of the comparator by taking the difference between the analog input signal and the feedback signal. So this feedback signal is the signal coming out from the ladder, which is a staircase reference voltage. And the error is detected at the control circuit, and the clock is allowed to advance towards the counter. So this error signal is very, very important here. Until there is some error signal, the clock will be in open state. And once this zero or error signal is go zero, completely zero, the clock is not allowed to advance, because the gate is closed. The counter advances in such a way as to reduce the error signal by increasing the feedback voltage. So here at the beginning, this will be more, analog input voltage will be more, and this reference voltage will be less. So because of this reason, the difference voltage will be more, or the error signal, the strength of the error signal will be high. As this reference voltage increases gradually in step manner, the strength of that error signal continuously decreases, and it becomes zero. The strength of the error signal becomes completely zero when this analog input voltage is exactly equal to this reference voltage or the feedback voltage coming from this binary ladder. So this is what happening here. So the error is detected by the control circuit, and the clock is allowed to advance towards the counter, and the counter advances in such a way as to reduce the error signal by increasing the feedback voltage. When the error is reduced to 0, the feedback voltage is equal to the analog input voltage, and the control circuitry stops the clock as the gate closes from advancing towards the counter, and the system comes to rest. So here, for every one cycle, which what we are calling as the count cycle, for every one cycle, the gate opens, the counter starts, then the gate closes, counter stops. So all these things happens at every cycle of the input voltage. And now we'll see what are the advantages of this counter type EDC. It is a very good method for converting an analog signal to a digital signal to a high resolution. So we can achieve here the higher resolution because it is an n-bit converter. It is called as the n-bit converter. Number of bits is not limited here, as the reference voltage is a variable one. You can increase the number of bits sufficiently. So as the number of bits increases, the resolution of the circuit generally high. So that is why it is a high resolution circuit. And it is simpler than the simultaneous method. In the last session, I have discussed the simultaneous method or simultaneous ADC. So it is a simpler to that. And what are the drawbacks? Conversion time is too high. It is in milliseconds. So this is the biggest problem. Or if you have a low frequency application, this you can use. But if you want to use this circuit at high frequency, you can't use it, because the conversion time is too high. That means the circuit takes long time. So one complete cycle, to convert one cycle, it takes millisecond. The time taken by the circuit is in milliseconds. So it is a very, very big time. So this is the biggest drawback. Because the time increases here, since it is of a higher value of higher bit circuit. Since it is a higher bit circuit. To improve the conversion time, one has to use the clock of higher frequency greater than 1 megahertz. You can increase the frequency of the clock so that this conversion time reduces, and the maximum conversion time, TC maxima, is given by this equation. TC max is equal to 2 raised to n minus 1 into T clock. So this is the T clock. So this is the T clock, means the time period of the clock, and where n is the number of bits. This n is the number of bits. So it is very clear. Thus, as the number of bits n increases, the conversion time also increases. 2 raised to n is there. For 2 bit, it is 2 raised to 2, 4. 4 minus 3, it becomes 3. And if it is a 4 bit, it is 2 raised to 4. 2 raised to 4, 2 into 2 into 2 into 2. 4, 8, 16. 16 minus 1 is 15. 16 minus 1 is 15. So the time suddenly or exponentially increases when this n or the number of bits increases. Other way to reduce the conversion time is to use of the clock of high frequency. So this clock, this here it is the time actually. So suppose if you are increasing the frequency, then it is a time period. So 1 by f is t. So if the f, the frequency becomes high, this becomes smaller. The t clock becomes smaller. So you can use a clock of high frequency more than 1 megahertz. But this works up to certain high frequency only. It may work up to 5 megahertz or 10 megahertz. If the frequency is further increases, the circuit won't work because the components used in the circuit should be compatible with such a high frequency. So beyond that, won't works as the components of the circuit won't support. So we can reduce this conversion time by increasing the frequency of the clock cycle, frequency of the clock. But the problem is that the components used in this circuit are capable of working only up to certain high frequency. If the frequency is going beyond that, the components won't work. So that is a problem. So you have to adjust. You have to adjust between the number of bits and the frequency, high frequency, to get a required or a what is that a nominal or a desired conversion time. A desired conversion time can be achieved by adjusting the clock of the cycle and by choosing the number of bits. So this is all about counter type of ADC, and it is very simple. Working is very simple. You can go through it. And write in the examination. Actually, I could explain this without the help of this writing matter, but this is prepared by keeping in mind about the students, because students need it to write in the examination. So that is why more writing part is there. Thanks for watching.